This is our first lesson on fluid mechanics, and it's going to be about density, pressure, Pascal's principle, and maybe we'll even get to Archimedes Principle at the end of the video. So we're going to start with density, and density is, I hope you watched the videos that I posted for you in the lesson before, but density is the conceptual videos, So the density is the relationship between the mass per volume. So the more mass you have per volume, the denser the material is. So density is measured in kilogram per meter cubic, and it has the letter rho, so this letter like this, called rho. And the good thing to know and remember is the density of water. It's 10 to the third kilogram per meter cubic. And then also there's such thing as specific gravity. Sometimes in the problems you may see something that is said like specific gravity. So specific gravity is the density of material compared to the water, because the material that is denser than water will sink, and the material that is lighter, not as dense as the water, will float. So there is specific gravity that defines whether the object is going to be floating or sinking. So if the specific gravity is greater than 1, then the material is going to be sinking. If it's less than 1, then the material is going to be floating. But if the specific gravity of an object is neither or equals to 1, it will neither float or sink. It will just hover in the liquid. Whenever in the place you place it, it just will stay in that position in the liquid. Also, the pressure is defined as force per unit area, where the force is understood to be the magnitude of the force acted perpendicular to the surface of the area. So the pressure is going to be measured in pascals or Newton per meter squared. So it's Newton per meter squared, or it has its own unit, and it is pascals. And atmospheric pressure, another number to remember. So atmospheric pressure is 1/10 to the 5th Pascal. So this is one of the number that I want you to remember. And the density of the water is 10 to the 3rd kilogram per meter cubic. So whenever you solve problems, these two values are important to know. Also, pressure is not a vector. It has only the magnitude. In other words, it's a scalar unit, not a vector. So pressure is defined as force per area, per unit area. And on the other hand, can pressure be enclosed in the fluid by pushing directly on the fluid? And the answer is yes, but it is much easier if the fluid is enclosed. The heat, for example, increases blood pressure by pushing directly on the blood, and in an enclosed system, like valves closed in the chamber. And if you try to push on the fluid in an open system, such as a river, the fluid flows away. So an enclosed fluid cannot flow away, and so the pressure is more easily increased by the applied force. So since atoms in the fluid are free to move about, they transmit the pressure in all parts of the fluid and to the walls of the container. And the pressure that is transmitted is said to be undiminished. And this phenomenon is called Pascal's Principle, or sometimes called Pascal's Law, because it is, Pascal was the first one, he was the French philosopher and the scientist in 1600s. And he was the first one to state this law. And so he said that a change in pressure applied to an enclosed fluid is transmitted undiminished in all portions of the fluid and to the walls of its container. So one of the most important technological applications of Pascal's principle is found in hydraulic system, which is enclosed fluid system used to exert the force. And the most common hydraulic system are those that operate the car brakes, or even at the dentist when they have to raise your chair when you're sitting on the chair. So they pushed on on the pedal and the chair is rising. So you change a little bit, you apply a little bit of force on a smaller area, and the bigger area changes the bigger force. So you can see from this picture that you see that actually, let's look at what the law states. So the law, Pascal's law, states that F1 over A1 is equal to F2 over A2. So if I apply F1 on the left side over the area 1, it equals to F2, the force that is applied on area 2 on the other side. But that force is much bigger, but the area is bigger as well. And this comes from because the pressure at one side is equal to the pressure on the other side. So the pressure here is equal to the pressure over here, because the pressure in the enclosed liquid system is undiminished. So I can say the force times the distance it compresses, force times the distance is the work, is equal to force times the distance on the other side. So I have force times the distance on one side and force times on the distance. So if I would pressure and move the piston this way, this much on one side, maybe it would move this much on the other side, but the work done on one side is equal to the work done on the other side. So the conservation of energy applied to hydraulic system tells us that the system cannot do more work than it is done on it. In other words, the work transmits energy, and so the work output cannot exceed the work input. And the power brakes and other similar hydraulic systems use pumps to supply extra energy when it is needed. Let's look at the first question. A waterbed is 2 meters on the side and 30 centimeters deep. Find the weight. So I have the density is equal to the mass per volume, and this is very important in many problems in this section. You will see this formula. So I can find the mass of this waterbed. The mass is equal to the density of the water times the volume. And the density of the water, if you remember, 10 to the third kilogram per meter cubic, and the volume is the waterbed has 2 meters on the side, so that means 2 by 2. The volume is the area, and times the height, which is 0.3. So I find that the mass is equal to 1200 kilogram. And they asked me about the weight, so they asked me about the force of gravity. So the weight is the same as force of gravity, so I times it by 10 mg, and that will be 12,000 newtons, or 12 kilonewtons. For the next question, they asked me to find the pressure. So the pressure is equal to how much force is applied per area, and in this case, force is the force of gravity. So I have the force of gravity per area. So from here, I get that the pressure is equal to the force of gravity is 12,000, and divide by the area, which is 2 times 2, because the sides of the bed are 2 by 2. So I get 3,000 or 3 kilopascals. So for the next question, they say in the car lift used in the service station, compressed air exerts a force on a small piston of circular cross section having the radius of R1 5 centimeters. This pressure is transmitted by an incompressible liquid to a second piston of radius R2 15 centimeters. What force must the compressed air exert on the small piston in order to lift the car weighing 13,300 newtons and neglect the weight of the pistons? So in this question, I know that the pressure on let's say here, the pressure here is equal to the pressure over here. So if these two pressures are equal to each other, I'm going to say P1 is equal to P2, and that is F1 over A1 is equal to F2 over A2. And then from here, I can say that F1 is equal to A1 over A2, F2. Now, if I plug in my numbers, it is circular, so I have pi r squared, r1 squared, which is 0.05 squared, divided by pi, and the other radius is 0.15 squared, and times the force that is applied, 13,300. So I get F1 is equal to 1.48 kilonewtons. And then for the second question, they ask what air pressure will produce a force of that magnitude. So if I am looking for the pressure, then for the second part, I'm going to say the pressure 1 is equal to F1 over A1. And then from here, I have the pressure 1 is equal to this, the force 1, divided by the area 1, which is pi times radius squared. And I get the pressure 1 is equal to 188.2 kilopascals. And for the last question, they ask you to show that the work done by the input is equal to the work done by the output piston, or they're the same. So let's say F1 pushed this much distance when the piston 1 was moved. So the volume of this area, or this volume, is equal to the volume that is rising on the other side. So this volume is going to be equal to this volume. And because the volume of one is equal to the volume of the other, I can say that A1 delta x1 is equal to A2 delta x2. This equation is also equal to 1 over A1 delta x1 equals to 1 over A2 delta x2. I can times both sides of the fractions by F1, F2, and F1 and F2. Then F1 over A1 is pressure, and F2 over A2 is also pressure. So this pressure is equal to that pressure, Pascal's principle. So those pressures can be cancelled. So what I have is left is F2 cross multiply delta x2 is equal to F1 delta x1. And this is the work done on the right side is equal to the work done on the left side. So that proves that the work done on one side is equal to the work done on the other side. Also, if your ears have ever popped in a plane when you flew on higher altitudes, or ached during a deep dive in a swimming pool, you have experienced the effect of the depth on pressure in the fluid. At the Earth's surface, the pressure exerts on you the pressure, the atmospheric pressure, or it's the weight of the air above you. And this pressure is reduced as you climb up in higher altitudes, and the air above you is not as dense, so there's less weight. And then under the water, the pressure exerted on your ears increases because now you not only have the pressure of the air above you, the atmospheric pressure, but you also have the pressure of the water on your ears. So in this case, the pressure is being exerted upon you is the result of both the weight of the water above you and the atmospheric pressure above you, or the atmosphere above you. You may have also noticed this effect of air pressure change when you're inside of the elevator, right, when you rise many stories, or when you need to dive 1 meter below the surface of the pool and feel pressure increase. So if we look at this image, let me make it green. So there is area 1. Well, area is the same for both the top and the bottom of the cylinder. So there is area 1 or area, and this is another area. So I'm gonna call this area and this area just A. And so let's talk about the pressure. So the pressure is equal to the force per area, and the forces that you're acting or you're experiencing on the top of the cylinder. So the force 1, the force on the top of the cylinder. So this is the force 1, and this is the force 2. So force 1 is equal to the so from here I can say, from this formula I can say the force is equal to the pressure times the area. So force 1 is equal to the atmospheric pressure times the area, because that's the area where it's acting on the top, plus, if you remember from the definition, the density of the water is equal to the mass per volume. So if I want to say the force acted by the water on the top of this area A, then I need mg, and mg is the same as rho g and times the volume. So I can rewrite it as rho of the water, g, and then the volume is the area times, and this height 1 by how much it is placed into the water, how deep it is placed in the water, h1. And then the same I can write for force 2. It's still the same atmospheric pressure times the area is the same. Then the density of the water is the same, g is the same, a is the same, but now it is h2, because the bottom of the cylinder is deeper. I'm going to derive the formula that you see here on the top, this formula. So and this is very important formula. So from here, if I divide every single term in this equation by A, I get F1 over A1, or A, is equal to atmospheric pressure plus rho, g, and h. So F1 over A1 is the pressure on the top. So that gives me pressure. And that is equal to, so if I want to calculate the pressure at every single height that I am looking at, so I have to include the atmospheric pressure, because there is pressure because of the atmosphere above the water. Then there is a pressure because of the water at each level. Maybe it's this line, or maybe I'm looking at this pressure, or maybe I'm looking at this pressure. So every time I have a different height to look at. And so this height is changing. So if you want to calculate pressure at any point in the water, all you have to do is the atmospheric pressure plus rho, g, and h. Rho is the density of water, g is gravitational acceleration, and h at what depth you're looking inside of the water. But coming back to our green formulas, the ones that we just derived. So change of the pressure between the top and bottom, or change of the force between the top and bottom, change of the force is equal to F2 minus F1, because H2 is longer than H1, so F2 has more force acting from the bottom than it is from the top. So it is equal to rho GA and H2 minus H1. And that is actually equal to rho g and the volume of the cylinder, because H2 minus H1 is the height of the cylinder, and A is the area, so A times the height will give me the volume. So that means this force is also has the name, and it's buoyancy force, and the buoyancy force is equal to rho G, and the volume. So if you watch the videos that I posted for you online for the lessons, the conceptual videos, then you might have heard that the buoyancy force is equal to the weight of the water or the liquid displaced or misplaced when an object is immersed in the water. So the water that is misplaced, let me write it, the mass is equal to the density times the volume from the definition of the density. So here you have the mass of the water, which is rho g, and then the volume of the cylinder. So if you place the cylinder inside of the water, how much water will rise? Or how much water, if it was out of the top, how much water would spill? So the spilling water would be equal to the water that is displaced by the cylinder, or in other words, it's the mass of the water times the volume of the cylinder. And this is a very important concept for the buoyancy force. So all you have to remember that the buoyancy force is equal to the weight of the water that is displaced by the object that is immersed inside of the water or any other liquid. And this leads us to Archimedes Principle, which states that the buoyant force is equal to the weight of the displaced water. In other words, the object will sink in the water or liquid to the level where the buoyancy force is equal to the weight of the object. And what you see here in the formula of the buoyancy, so B or FB, sometimes it's going to be force of buoyancy, FB, is equal to the pressure between the bottom and the top times the area. So the pressure times the area is equal to the force, and buoyancy is a force. It equals to the weight of the liquid displaced by the or misplaced by the object that is immersed in the water. Let's look at our first question in using Archimedes Principle. In this question, we have a famous story about the crown that Archimedes used to calculate the density of the crown to figure out whether it was gold or not. And so in this case, we have our bargain hunter purchases a gold crown at a flea market. After she gets home, she hangs it from a scale and finds its weight to be 7.84 newtons. She then weighs the crown while it is immersed in water, and now the scale reads 686 newtons. Is the crown made of pure gold? So Archimedes' story states that when he was given this crown problem by the king, he came home and he didn't know how to solve it. And then when he sat down in the bath, which is, we do not know if the story is true or not, when he sat down in the bath, he realized that the water that spilled out of the bathtub is actually equal, the volume is equal to his body. So the volume times the density will give me the mass of the water that was displaced. So the water that is spilled around the tub is equal to the volume of the one that he displaced when he got in the tub. So we're going to use this principle, the same principle, to solve the question about the crown. So the information we have here is the weight of the crown before and after it was placed in the water, and the buoyancy force is the difference between these two weights. So if I subtract these two, I will get that the buoyancy is equal to 0.98 newtons, and that is equal to the mass of the water and weight of the water. So that's, I know that is the weight of the water that is displaced by the crown is equal to this much, because the difference between those two forces is the buoyancy force. Now the weight of the water is equal to the density of the water times the volume and times g. So that's the weight of the water. It's the mass times g. So we have the mass of the water times g, and equals to 0.98. So that means rho of the water times the volume is equal to 0.098 if I divide both sides by g. And then I find that the volume of the water, or the volume of the crown, because it's the same volume for both, is equal to 98 10 to the negative 6 meter cubic. So I have this part and the buoyancy and the weight of the water. So this is in newtons. And then I go to this step. And then from here, I see that I can figure out the density of the crown because I know the volume of the crown now. So the weight of the crown in the air is 784 newtons. That means the mass of the crown is 0.784 kilogram. And that is equal to the density of the crown times the volume of the crown. But the volume of the crown and the volume of displaced water are equal to each other. So I have the density of the crown is equal to 0.784 divided by the volume of the crown, which is 9810 to the negative 6. And I get the density of the crown is 8,000 kilogram per meter cubic. And if I compare this number 8,000 kilogram per meter cubic with the density of the gold by the table that is given for every single element, different density. So my answer for density for gold was 8,000, but in reality it should be 19.310 to the third kilogram per meter cubic. So that means the crown was not made of gold. Here's another question related to Archimedes principle, and in this case we have an iceberg floating in seawater is extremely dangerous because most of the ice is below the surface. The hidden ice can damage a ship that is still a considerable distance away from the visible ice. What fraction of iceberg lies below the seawater level? And the density of the water, seawater, is given, and the density of the ice is given. So it is floating because there is a buoyancy force, and the buoyancy force is equal to the water that is displaced by the iceberg, which is the rho of the water, the mass, times the volume of the ice that is in, and times g. And because it's floating, the buoyancy force is equal to the weight of the iceberg itself. So from here I know that the mass of the iceberg, which is rho of the iceberg, times the volume of the iceberg times g are both equal to each other, because the mg, which is the mass of the iceberg times the volume of the iceberg times g, is equal to the buoyancy force. So that is the buoyancy force. And this is the mass of displaced water times g. I can cancel g from both sides, and what I get is the volume in over the volume of iceberg is equal to rho of the iceberg over density of the water, rho of the water. And that will give me 917 divided by 1030. And that will be equal to 0.89 or 89%. So that means 89% of the iceberg is inside of the water, and only 11% of the iceberg is out. So 11% of the iceberg is visible, and 89% of the iceberg is inside of the water. I will stop our first video on fluid mechanics at this point, and thank you for watching this one, and I'll see you in the next one.